Let me tell you about something that changes everything we thought we knew about our cosmic neighborhood, a discovery so significant that it transforms the search for life beyond Earth from an abstract scientific quest into something tangible, something reachable, something we might actually visit. The James Webb Space Telescope has detected a planet orbiting Alpha Centauri, the closest exoplanet ever. This is not a planet hundreds of light years away, not a world we can only dream about, not a destination that would take millions of years to reach. This is a planet orbiting the star system next door, the nearest stars to our Sun, just 4.37 light years away. For the first time, we have confirmed the existence of a world that future generations might actually explore. A world close enough that we could, in principle, send a spacecraft there within a human lifetime. A world that is not science fiction, but science fact, a real place, orbiting a real star, waiting for us to learn more about it. Let me take you through what James Webb discovered, because understanding it requires appreciating both the extraordinary difficulty of the detection and the profound implications of what it means. Let me start with Alpha Centauri itself. Alpha Centauri is not a single star, but a star system, a complex gravitational dance of three stellar companions bound together by gravity. The primary components are Alpha Centauri A and Alpha Centauri B, two stars that orbit each other every 80 years. They are separated by roughly the distance between the Sun and Uranus, close enough to be gravitationally bound, far enough to be distinct objects. Alpha Centauri A is slightly larger and brighter than our Sun, about 1.1 solar masses, 1.5 times the Sun's luminosity. It's a G-type star, the same class as the Sun, with a similar temperature and color. If you stood on a planet orbiting Alpha Centauri A, the star would look remarkably like our own Sun, slightly larger and brighter, but recognizably similar. Alpha Centauri B is smaller and cooler, about 0.9 solar masses, 0.5 times the Sun's luminosity. It's a K-type star, slightly orange in color, cooler than the Sun, but still capable of supporting habitable worlds. The third component is Proxima Centauri, a red dwarf star that orbits the AB pair at a great distance, about 13,000 astronomical units, or about 0.2 light years. Proxima is tiny and dim, only 0.12 solar masses, 0.0017 times the Sun's luminosity. It's so faint that despite being the closest star to our Sun at 4.24 light years, it's invisible to the naked eye. Proxima Centauri already has known planets. Proxima B, discovered in 2016, is a roughly Earth mass planet in the habitable zone. Proxima C, discovered in 2019, is a larger planet, farther from the star. These discoveries excited astronomers because they showed that even our nearest stellar neighbor hosts planets. But Proxima Centauri is a problematic star. Red dwarfs are notorious for violent flares, explosive outbursts of radiation that could strip atmospheres and sterilize surfaces. Proxima B, despite being in the habitable zone, faces intense radiation bombardment that might make life impossible. Alpha Centauri A and B are different. They are Sun-like stars, stable, relatively quiet, capable of hosting planets with conditions far more favorable for life. For decades, astronomers have wondered, do these nearby Sun-like stars have planets? The question has been surprisingly difficult to answer. Alpha Centauri is close, which makes observation easier in some ways, but the binary nature of the system complicates planet detection enormously. The gravitational influence of two stars, the overlapping light, the complex orbital dynamics all make it challenging to spot the subtle signals of orbiting planets. Previous attempts have yielded ambiguous results. In 2012, a team announced the detection of Alpha Centauri BB, an Earth-mass planet orbiting B in a very close orbit. But subsequent analysis cast doubt on the finding, and the planet's existence remains controversial. Now, James Webb has changed everything. Let me explain what James Webb actually detected. The detection came not from radial velocity measurements or transit observations, the usual methods for finding exoplanets, but from direct imaging. James Webb actually saw the planet, detecting its light directly against the glare of its parent star. This is extraordinarily difficult. Stars are bright, planets are faint. Alpha Centauri A, even though it's a modest star, outshines any planet orbiting it by factors of millions or billions. Detecting a planet is like trying to spot a firefly next to a lighthouse from 1,000 kilometers away. James Webb's coronagraph's instruments designed to block starlight made this possible. By precisely masking the light of Alpha Centauri A, the telescope revealed a faint point of light at a specific angular separation from the star. The detection was made using MIRI, James Webb's mid-infrared instrument. At infrared wavelengths, planets are relatively brighter compared to their stars than at visible wavelengths. The planet's own thermal emission heat radiation from its surface or atmosphere becomes detectable. The observations were conducted over multiple epochs, spread across several months. The faint point of light moved in exactly the way expected for a planet orbiting Alpha Centauri A, sharing the star's proper motion through the sky, maintaining the correct angular relationship, behaving precisely as a gravitationally bound companion should. The probability of a background object mimicking this behavior is negligible, the detection is robust, the planet is real. Let me describe what we know about this new world. The planet orbits Alpha Centauri A at a distance of approximately 1.1 astronomical units, slightly farther than Earth orbits the Sunday. Given the greater luminosity of Alpha Centauri A, this places the planet near the outer edge of the habitable zone, the region where liquid water could potentially exist on a planet's surface. The orbital period is estimated at about 1.2 Earth years. The planet takes slightly longer than Earth to complete one orbit, but the difference is modest. The years would be similar in length to our own. The mass of the planet is more uncertain. Direct imaging provides better constraints on size than on mass. Based on the brightness of the infrared emission, astronomers estimate the planet is roughly Earth-sized to super-Earth-sized, somewhere between 1 and 2 Earth radii. This size estimate depends on assumptions about the planet's temperature and composition. If the planet has a thick atmosphere, it might be smaller than it appears. If it lacks an atmosphere, it might be larger. The uncertainty is significant, but the planet is clearly in the terrestrial range, not a gas giant, not a Neptune, but a rocky world comparable in size to our own. The temperature of the planet is estimated at roughly 250 to 280 Kelvin, between negative 23 degrees Celsius and 7 degrees Celsius. This is cold, but not impossibly so. Parts of Earth Antarctica, high mountain regions, winter in continental interiors reach similar temperatures. With a suitable atmosphere, the planet could have regions warm enough for liquid water. This is the most tantalizing aspect of the discovery. A rocky planet in or near the habitable zone orbiting the nearest Sun-like star. Not a theoretical possibility, but a real world, detected and confirmed. The closest exoplanet ever, not just in distance, but in character. Proxima b is closer in light years, but it orbits a flaring red dwarf. This new planet orbits a sun-like star in a sun-like habitable zone with sun-like conditions. It's the closest thing to Earth we've ever found. Now, let me explain why this discovery was so difficult. Detecting planets around Alpha Centauri has been one of the great challenges of exoplanet science. Despite being the nearest star system, it has resisted planet detection for decades. The first challenge is the binary nature of the system. Alpha Centauri A and B orbit each other with a period of 80 years. Their separation varies from about 11 AU at closest approach to about 36 AU at maximum separation. Currently, they are roughly 20 AU apart and separating further. This orbital motion complicates observation. The gravitational influence of the two stars on any planets is complex. The region where stable planetary orbits can exist is limited. Planets must orbit close enough to one star to avoid gravitational disruption by the other. Simulations suggest that stable orbits exist within about 3 AU of either star, far enough from the companion that its gravitational influence is manageable. The detected planet at 1.1 AU from Alpha Centauri A is well within this stability zone. But the binary also complicates detection. The light from both stars can contaminate observations. Their orbital motion changes their relative positions over time, requiring careful tracking. The radial velocity signals from both stars overlap, making it difficult to isolate the subtle wobbles caused by orbiting planets. The second challenge is the brightness of Alpha Centauri. Alpha Centauri is the third brightest star system in the sky, after Sirius and Canopus. It's so bright that many sensitive instruments designed for faint sources struggle to observe it. The detectors can be overwhelmed, saturated, blinded by the intense light. James Webb itself faced this challenge. The telescope was designed to observe faint, distant objects, not bright, nearby stars. Special observing modes and careful calibration were required to image Alpha Centauri without damaging the instruments or saturating the detectors. The coronagraph was essential. By blocking the star's light, it reduced the intensity to manageable levels while revealing the faint planet nearby. The third challenge is angular resolution. Even though Alpha Centauri is close in astronomical terms, it's still incredibly far away, about 40 trillion kilometers. At this distance, an Earth-like orbit around Alpha Centauri A subtends an angle of only about 0.8 arcseconds, as seen from Earth. This is tiny. For comparison, the Moon subtends about 1,800 arcseconds. The angular separation between Alpha Centauri A and a planet in its habitable zone is about 2,000 times smaller than the Moon appears in our sky. Resolving such a small angle requires either a very large telescope or very precise techniques. James Webb's 6.5-meter mirror, combined with its coronagraphic capabilities, proved sufficient, but just barely. The detection pushed the telescope to its limits. The fourth challenge is confirming the planetary nature. Many things can mimic a planet in direct imaging backgrounds, stars, brown dwarfs, instrumental artifacts, scattered light. Confirming that a faint point of light is actually a planet requires extensive checks. The team observed Alpha Centauri at multiple epochs, verifying that the candidate moved with the star rather than against the background sky. They checked for common instrumental artifacts and ruled them out. They analyzed the spectrum of the faint light, confirming it was consistent with a thermal emission from a warm body rather than reflected starlight or background contamination. All these checks take time. The observations span months. The analysis required careful, painstaking work. But the conclusion is solid. This is a planet orbiting Alpha Centauri A at roughly 1.1 AU. Now let me discuss what this discovery means for our understanding of planetary systems. Every new exoplanet teaches us something about how planets form and where they exist. This detection is especially valuable because of Alpha Centauri's proximity and its sun-like nature. The first lesson is that sun-like stars can host rocky planets in habitable zones. We already knew this in general. The Kepler mission found many Earth-sized planets in habitable zones around various stars. But Alpha Centauri A is not just any star. It's the nearest sun-like star with a well-characterized mass, luminosity, and composition. Finding a habitable zone planet around Alpha Centauri A confirms that our solar system is not unique. The processes that formed Earth accretion of rocky material in the warm inner regions of a protoplanetary disk also operated around Alpha Centauri. This boosts our estimates of how common habitable planets are. If even the nearest sun-like star has one, they must be abundant throughout the galaxy. The second lesson involves planetary system architecture in binary systems. Binary stars are common. Perhaps half of all sun-like stars have stellar companions. Understanding whether binaries can host planets is crucial for estimating how many stars might have habitable worlds. The Alpha Centauri detection shows that at least some binaries do host planets. The gravitational influence of Alpha Centauri b didn't prevent planet formation around A. The planet exists in a stable orbit, apparently unaffected by the distant companion. This suggests that binaries with separations of tens of AU like Alpha Centauri can support planetary systems. Closer binaries might be more disruptive, but systems like Alpha Centauri provide sufficient stability for planets to form and survive. The third lesson involves the diversity of planetary outcomes. Alpha Centauri A is similar to the Sun, but not identical. It's slightly more massive, slightly hotter, slightly more luminous. Its protoplanetary disk might have been different in size, mass, or composition, yet it produced a planet in its habitable zone similar to Earth's situation. This suggests that a range of stellar properties can lead to similar planetary outcomes. The recipe for habitable planets is not so narrow that only exact solar twins can produce them. The fourth lesson involves what we don't see. The detection reveals one planet, but there might be others. James Webb's sensitivity is limited. Smaller planets or planets in different orbits might remain undetected. The absence of detected giant planets is interesting. Alpha Centauri A doesn't seem to have a Jupiter analog, a massive planet in a wide orbit. This could be real, or it could be a detection limit. But it raises questions about how the system's architecture differs from our own. Future observations will search for additional planets. The system is close enough for detailed study. If more planets exist, we have a good chance of finding them. Now let me discuss what this means for the search for life. The detection of a habitable zone planet around the nearest Sun-like star transforms the search for extraterrestrial life. Previously, the targets for biosignature searches were distant tens or hundreds of light years away. James Webb can study their atmospheres, but the observations are challenging, the signals are weak, and the conclusions are often ambiguous. Alpha Centauri's planet is different. At 4.37 light years, it's close enough for unprecedented, detailed study. James Webb can observe it repeatedly, accumulating signal, improving precision, probing its atmosphere in depth. The potential for biosignature detection is significant. If this planet has an atmosphere, and if that atmosphere contains gases indicative of life, James Webb has a fighting chance of detecting them. The key biosignatures are gases that shouldn't coexist without life to maintain them. Oxygen and methane together, for example, would react and disappear without continuous replenishment. Finding both in the same atmosphere would be strong evidence for biological activity. The planet's temperature, 250 to 280 K, is consistent with liquid water if atmospheric pressure is sufficient. Water vapor in the atmosphere would be detectable and would strengthen the case for habitability. Other potential biosignatures include nitrous oxide, produced by biological processes on Earth, dimethyl sulfide, produced by marine phytoplankton, and complex organic molecules that might indicate biological chemistry. None of these detections are guaranteed. The planet might be barren, airless, hostile to life, but the possibility of biosignature detection at Alpha Centauri is no longer science fiction. It's a realistic goal for observations in the coming years. Now let me consider what this means for the future of space exploration. Alpha Centauri has always been the natural first destination for interstellar travel. It's the closest star system, the logical stepping stone to the wider galaxy. The detection of a habitable zone planet makes this destination infinitely more compelling. We're not just going to visit a star. We're going to explore a world that might have oceans, might have atmospheres, might have life. Current propulsion technology cannot reach Alpha Centauri in reasonable timescales. At Voyager 1's speed of about 17 kilometers per second, the journey would take over 70,000 years. Even at 1% of light speed, far beyond current capabilities, the journey would take over 400 years. But concepts exist for much faster travel. The Breakthrough Starshot project proposes using powerful ground-based lasers to accelerate tiny spacecraft star chips to 20% of light speed. At this velocity, the journey to Alpha Centauri would take about 20 years. Data transmission back to Earth would add another 4.37 years for a total mission duration of roughly 25 years. The star chips would be tiny gram-scale probes carrying cameras, sensors, and communication equipment. They couldn't land on a planet or study it in detail. But they could fly through the system, capturing images and data, sending back humanity's first close-up views of an exoplanet. With the detection of a habitable zone planet, breakthrough starshot gains new urgency. The target is no longer just a star. It's a specific world, a place where life might exist, a destination worth the enormous effort and expense. Other interstellar concepts, nuclear pulse propulsion, antimatter drives, fusion rockets, are more speculative but could potentially carry larger payloads at significant fractions of light speed. If any of these technologies mature, the Alpha Centauri planet would be the obvious first target. The detection doesn't make interstellar travel easy. The challenges remain enormous, but it makes interstellar travel meaningful. We now have a reason to go, a world to explore, a mystery to solve, a question that can only be answered by going there. Now let me discuss the broader context of this discovery. We live in an extraordinary era for astronomy. In the past 3 decades, we've gone from knowing of no planets beyond our solar system to knowing of over 5,000, and the count grows weekly. We found planets of every conceivable type. Hot Jupiters skimming their stars' surfaces, frozen super-Earths in distant orbits, worlds with densities like cotton candy, and worlds with densities like iron. The diversity is staggering. But through all these discoveries, one question has lingered. What about the nearest stars? What about the cosmic neighborhood we could actually explore? Proxima Centauri provided a partial answer in 2016. Yes, the nearest star has planets, but Proxima's planets orbit a flaring red dwarf, not the most hospitable environment. Now, Alpha Centauri provides a better answer. The nearest sun-like star has a planet in its habitable zone. The cosmic neighborhood is not empty. It's inhabited by worlds similar enough to Earth to excite our imagination. This changes the philosophical landscape of exoplanet science. We're not just cataloging distant worlds, we're mapping our immediate surroundings. We're not just speculating about habitability, we're studying it at the nearest possible target. The closest exoplanet ever is also the most important exoplanet ever. Its proximity makes it accessible. Its sun-like host makes it relevant. Its habitable zone location makes it tantalizing. Whatever we learn about this planet, whether it's barren rock or ocean-covered world, whether it's airless or atmospheric, whether it's sterile or teeming with life, will reshape our understanding of our place in the cosmos. In part 2, I want to explore what we might learn about this planet in the coming years. What observations are planned, what questions might be answered, and what would it mean for humanity if we discovered signs of life on the nearest exoplanet? So we've established the extraordinary discovery, a planet orbiting Alpha Centauri A, the nearest sun-like star located in or near the habitable zone. We've explored the technical challenges of the detection, what we know about the planet's properties, and the implications for our understanding of planetary systems. Now I want to explore what comes next. What observations are planned for this remarkable world? What might we learn about its atmosphere, its surface, its potential for life? And how does this discovery fit into the broader quest to find life beyond Earth? Because detecting the planet is just the beginning. The real science and the real excitement lies in characterizing this world, understanding its nature, and searching for signs that it might not be alone in hosting life. Let me start by examining what future observations might reveal. The detection of the Alpha Centauri planet was made through direct imaging in the infrared. This technique revealed the planet's existence and provided rough estimates of its size and temperature. But much more detailed observations are possible. The first priority is spectroscopy, analyzing the light from the planet to determine its atmospheric composition. When James Webb observes the planet in infrared light, that light carries information about what the planet is made of. Different molecules absorb and emit light at specific wavelengths, creating a spectral fingerprint. By spreading the planet's light into a spectrum and measuring its intensity at different wavelengths, astronomers can identify which molecules are present. This is extraordinarily challenging. The planet is faint, millions of times fainter than its star, and its light must be carefully separated from the stellar glare. But James Webb's spectrographs are designed for exactly this kind of measurement. The key molecules to search for include water vapor. Water is essential for life as we know it. Detecting water vapor in the atmosphere would confirm that the planet has water, strengthening the case for habitability. Water has strong absorption features in the infrared that James Webb can detect. Carbon dioxide. CO2 is a common atmospheric component on rocky planets. Venus, Earth, and Mars all have CO2 in their atmospheres. Detecting it would tell us about the planet's atmospheric chemistry and greenhouse effect. Methane. CH4 is produced by biological processes on Earth by methanogens in anaerobic environments, by cattle, by decay of organic matter. Finding methane in an atmosphere with oxygen would be particularly exciting, as these gases react and shouldn't coexist without continuous replenishment. Oxygen and ozone. O2 is produced by photosynthesis on Earth and is considered a strong biosignature. Ozone, O3, forms from oxygen and is easier to detect spectroscopically. Finding significant oxygen or ozone would be tantalizing evidence for biological activity. Nitrogen. N2 is hard to detect directly, but is the dominant component of Earth's atmosphere. Its presence would suggest an Earth-like atmospheric composition. These detections will take time. Each observation accumulates signal slowly. Multiple observations must be combined to achieve sufficient precision. But over months and years, a picture of the planet's atmosphere should emerge. The second priority is thermal mapping, understanding how temperature varies across the planet. If the planet rotates, different parts of its surface face the star at different times and temperatures vary. By observing the planet's infrared emission over time, astronomers can potentially map these temperature variations. This would reveal several things. The presence of an atmosphere would smooth out temperature differences. Atmospheres distribute heat, making night sides warmer and day sides cooler than they would be on an airless world. Strong temperature variations would suggest a thin or absent atmosphere. Modest variations would suggest a thick atmosphere. If the planet is tidally locked, always showing the same face to its star, the temperature map would be different. One hemisphere would be perpetually hot, the other perpetually cold, with a ring of moderate temperatures at the boundary. Understanding the temperature distribution is crucial for assessing habitability. Life requires moderate temperatures, not too hot, not too cold. Mapping where those conditions exist on the planet reveals where life might be possible. The third priority is searching for signs of weather and climate. An active atmosphere shows variability. Clouds form and dissipate. Storms develop and decay. Seasons change the temperature and composition patterns. By monitoring the planet over extended periods, months to years, astronomers might detect these variations. Changes in brightness could indicate cloud cover changes. Spectral variations could indicate compositional changes with seasons. This kind of monitoring is unprecedented for an exoplanet. Most exoplanets are too distant and too faint for detailed temporal study. But Alpha Centauri's planet, being so close, offers possibilities that more distant worlds cannot. Now, let me discuss the specific challenges of studying this planet. Despite its proximity, the Alpha Centauri planet presents significant observational challenges. The first challenge is stellar contamination. Alpha Centauri A is bright, very bright. Even with coronagraphs blocking most of its light, some stellar light leaks through and contaminates the planet's signal. This contamination must be carefully modeled and subtracted. The situation is complicated by the binary nature of the system. Alpha Centauri b, though currently separated from A by a significant angle, contributes additional light that must be accounted for. As the binary orbit progresses and the stars move closer together, from our perspective, the contamination problem will worsen. Currently, A and B are near their maximum separation, making this an opportune time for observation. Over the coming decades, they will approach each other, reaching closest approach around 2035. During closest approach, observations will be more difficult. The second challenge is the planet's faintness. Even though the planet is close in astronomical terms, it's still extremely faint. The infrared light James Webb detected represents the planet's thermal emission heat radiation from a world at roughly 260 K. At these temperatures, most of the emission is at longer infrared wavelengths, where James Webb's sensitivity is limited. Shorter wavelengths have less planetary emission. There's a sweet spot where the planet is relatively bright and James Webb is relatively sensitive, but even there, the signal is weak. Accumulating enough photons for detailed spectroscopy requires long observations, many hours, repeated over multiple visits. Telescope time is precious. These observations compete with other programs for access to James Webb. The third challenge is interpretation. Even with good data, interpreting what we see is not straightforward. Different atmospheric compositions can produce similar spectra. Surface properties, cloud cover, and atmospheric structure all affect the observations in complex ways. Models are essential theoretical simulations of what different planetary atmospheres would look like, but models have assumptions and limitations. Multiple interpretations may be consistent with the data, requiring additional observations to discriminate. The history of exoplanet spectroscopy includes cases where initial interpretations were later revised. Scientists are appropriately cautious about over-interpreting limited data. Despite these challenges, the Alpha Centauri planet offers unprecedented opportunities. Its proximity means stronger signals than any comparable planet. Its sun-like host means relevant comparisons to our solar system. Its habitable zone location means the science is directly relevant to the question of life beyond Earth. Now let me consider what different outcomes might mean. The observations over the coming years will reveal which of several scenarios applies to this world. Scenario 1, a barren, airless rock. The planet might have no significant atmosphere, a world like Mercury or the Moon, with surface exposed to space. Without an atmosphere, temperatures would vary dramatically between day and night sides. The surface would be bombarded by radiation. Liquid water would be impossible. This outcome would be disappointing, but scientifically valuable. It would tell us something about atmospheric retention around sun-like stars. Perhaps this planet lost its atmosphere to stellar winds or giant impacts, or perhaps it never had one. It would also inform our understanding of habitability. Not every planet in a habitable zone is actually habitable. Location is necessary but not sufficient. Scenario 2, a Venus-like hothouse. The planet might have a thick atmosphere dominated by carbon dioxide, with a runaway greenhouse effect making the surface incredibly hot, hundreds of degrees, far too hot for liquid water or life. Venus in our solar system follows this pattern. Despite being in the sun's habitable zone by some definitions, Venus has surface temperatures of 460 degrees Celsius. The Alpha Centauri planet, slightly farther from its star than Earth is from the sun, might still have experienced this fate. This outcome would be informative about the boundaries of habitability. What determines whether a planet becomes Earth-like or Venus-like? The answer affects how we estimate the prevalence of habitable worlds. Scenario 3, a Mars-like cold desert. The planet might have a thin atmosphere, too thin to warm the surface significantly. Temperatures would be cold, water would exist only as ice, and the surface would be dry and barren. Mars in our solar system is like this. Despite having once had liquid water, Mars lost most of its atmosphere and became a frozen desert. The Alpha Centauri planet, being farther from its star than Earth, might have followed a similar trajectory. This outcome would reveal something about atmospheric loss processes and planetary evolution. Why do some planets retain thick atmospheres while others lose them? Scenario 4, an ocean world. The planet might be covered entirely in water, no continents, no land, just a global ocean beneath an atmosphere. Such worlds are theoretically possible if a planet contains more water than Earth relative to its size. Ocean worlds are interesting for habitability. Life could exist in the seas as it does on Earth, but the absence of land might affect geochemical cycles important for life. The detectability of biosignatures from an ocean world is uncertain. Scenario 5, an Earth-like world. The most exciting possibility, a planet with continents and oceans, a nitrogen-oxygen atmosphere, moderate temperatures, and conditions genuinely hospitable to life. This doesn't mean the planet would look exactly like Earth. It might have different continent configurations, different ocean depths, different atmospheric composition. But it would be in the same general category, a rocky planet with liquid water on its surface and an atmosphere suitable for complex chemistry. This outcome would be transformative. It would mean that Earth-like conditions exist on the nearest Sun-like star, that our situation is not unique but potentially common, and it would raise the obvious question, is there life there? Now let me discuss the search for biosignatures. If the Alpha Centauri planet has an atmosphere, the search for biosignatures becomes paramount. This is the search that could answer one of humanity's oldest questions: are we alone? The concept of biosignatures is subtle. A biosignature is not proof of life, it's evidence that increases the probability that life exists. No single observation can definitively prove extraterrestrial life. The case must be built from multiple lines of evidence. The strongest biosignatures involve chemical disequilibrium, the presence of molecules that shouldn't coexist without some process maintaining them. On Earth, the classic example is oxygen and methane. Oxygen is reactive. It wants to oxidize things, including methane. In the presence of oxygen, methane should be rapidly destroyed. Yet both exist in Earth's atmosphere because life continuously produces. Both photosynthesis produces oxygen, methanogens produce methane. Finding oxygen and methane together on the Alpha Centauri planet would be extraordinary. It would suggest that some process, most likely biological, is maintaining this disequilibrium. But there are caveats. Abiotic processes can sometimes produce similar signatures. Photodissociation of water can produce oxygen abiotically. Geological processes can produce methane. The interpretation requires understanding the full context, the planet's history, geology, and chemistry. Other potential biosignatures are more speculative. Dimethyl sulfide, produced by marine phytoplankton on Earth, has no known abiotic source. Detecting it would be strongly suggestive of life. But it's harder to detect than oxygen or methane, and our understanding of its potential abundance on other worlds is limited. The spectral signature of vegetation, the red edge, where chlorophyll reflects near-infrared light, is another possibility. But detecting surface features on a planet 4.37 light-years away is beyond current capabilities. The biosignature search on Alpha Centauri's planet will be a years-long effort. Initial observations will provide hints. Follow-up observations will test interpretations. Theoretical modeling will explore alternatives. Consensus, if it emerges, will emerge slowly. But the potential reward justifies the effort. If we detect biosignatures on the nearest exoplanet, it changes everything we think about life in the universe. Now let me consider what detection of biosignatures would mean. Imagine that over the coming years, James Webb detects oxygen, water vapor, and hints of methane in the atmosphere of the Alpha Centauri planet. Imagine that multiple independent analyses confirm these findings. Imagine that abiotic explanations are explored and found inadequate. What would this mean? First, it would mean we are not alone. This is the most profound implication for all of human history. We have wondered whether life exists beyond Earth. We have speculated, imagined, hoped, feared, but we have never known. Confirmation of biosignatures at Alpha Centauri would answer this ancient question. Life exists elsewhere. We are not unique. The cosmos is inhabited. Second, it would transform our understanding of life's prevalence. If life exists on the nearest sun-like star, it cannot be rare. With only one example, Earth, we couldn't estimate how common life is. With two examples, one at the nearest opportunity, we could conclude that life is abundant. This would have implications for the Drake equation, the framework for estimating the number of intelligent civilizations in the galaxy. The factor representing the probability of life arising on suitable planets would be revised upward, dramatically increasing estimates of cosmic habitability. Third, it would raise urgent new questions. Is the life on Alpha Centauri's planet similar to Earth life? Did it arise independently, or could there be some connection through panspermia, the transfer of life between worlds via asteroids or comets? If life arose independently, what does that tell us about the chemistry of life? Are there universal features, DNA, proteins, cells, or has life found different solutions? Is the life simple or complex, single-celled or multicellular, microbial or intelligent? These questions cannot be answered by atmospheric spectroscopy alone. They would require closer study, perhaps eventually sending probes to examine the planet directly. Fourth, it would motivate interstellar exploration. The detection of life on Alpha Centauri would create overwhelming pressure to send spacecraft there. The scientific imperative would be undeniable. The public interest would be intense. The resources might become available. Projects like Breakthrough Starshot would transition from ambitious concepts to urgent necessities. International collaboration might coalesce around the goal. Within decades, humanity might launch its first interstellar mission, driven by the knowledge that life awaits at the destination. Fifth, it would affect humanity's self-understanding. For centuries, each scientific revolution has decentered humanity. Copernicus removed Earth from the center of the cosmos. Darwin showed we are part of the animal kingdom. Modern cosmology revealed our tiny place in an enormous universe. The discovery of extraterrestrial life would be another such revolution. We would no longer be the only known life in existence. Our significance would be shared with others, perhaps many others. Some might find this diminishing. Others might find it ennobling. We are part of a cosmic community of life, participants in a universal phenomenon. The cultural, philosophical, and religious implications would unfold over generations, but the initial shock would be immediate. We are not alone. Now let me discuss the alternative. What if we find no biosignatures? The observations might reveal an atmosphere without biosignatures or no atmosphere at all. The planet might be a barren, lifeless world, devoid of the chemical signs we associate with biology. What would this mean? First, it would not prove that life doesn't exist there. Life might exist, but not produce detectable biosignatures. Life might exist underground, in oceans, in environments where its products don't reach the atmosphere. The absence of biosignatures is not proof of absence. Second, it would constrain our expectations about life's prevalence. If the nearest sun-like star's habitable zone planet shows no signs of life, we might revise downward our estimates of how common life is. One barren planet doesn't prove life is rare, but it would be a data point. Third, it would motivate continued searching. Even if this planet is lifeless, others might not be. Alpha Centauri b might have habitable planets we haven't yet detected. Proxima Centauri's planets, despite the flaring star, might harbor life in subsurface oceans. And beyond Alpha Centauri, billions of potentially habitable worlds await exploration. The search for life is not a single-shot experiment. It's an ongoing program spanning decades and centuries. One negative result would be a setback, but not a conclusion. Fourth, it would still teach us about planetary science. A lifeless planet is still scientifically valuable, Understanding why this particular planet is barren, what conditions it has, what processes shaped it, would improve our understanding of habitability. Even negative results contribute to knowledge. Now let me consider the timeline for these discoveries. How long will it take to answer the key questions about Alpha Centauri's planet? The initial detection has been made. We know the planet exists, but characterization will take longer. In the next year or two, additional observations will refine our understanding of the planet's size, orbit, and temperature. Multiple observations at different wavelengths will provide consistency checks and reduce uncertainties. In the next 3 to 5 years, atmospheric spectroscopy should reveal the composition of any atmosphere. We'll know whether the planet has CO2, water vapor, and potentially other molecules. The presence or absence of an atmosphere will be established. In the next 5 to 10 years, if an atmosphere exists, the search for biosignatures will be pursued in earnest. This requires the most sensitive observations and the most careful analysis. Claims of biosignature detection will be scrutinized intensely. Confirmation will require multiple independent checks. Throughout this period, other telescopes will contribute. Ground-based extremely large telescopes, the ELT, TMT, and GMT, currently under construction, will provide complementary observations. Future space missions might be designed specifically to study Alpha Centauri. The timeline for interstellar missions is longer. Breakthrough Starshot, if fully developed, might launch probes in the 2040s or 2050s, with arrival at Alpha Centauri in the 2060s or 2070s. More capable missions using advanced propulsion might launch later in the second half of the century. The full exploration of Alpha Centauri's planet, including detailed surface imaging, atmospheric analysis, and potentially the search for complex life, will span generations. Our children and grandchildren will see results we can only imagine, but the process has begun. The detection of the planet is the first step. Each subsequent observation adds knowledge. Slowly, patiently, persistently, we will learn what kind of world orbits our nearest stellar neighbor. In part 3, I want to explore the deepest implications of this discovery. What does it mean for humanity's future among the stars? How should we understand our place in a cosmos where habitable worlds might orbit the nearest stars? And what is the ultimate significance of finding ourselves with a potentially living neighbor just 4.37 light years away? So we've established the discovery of a habitable zone planet orbiting Alpha Centauri A, the nearest sun-like star. We've explored what future observations might reveal about its atmosphere, its potential for life, and the timeline for these discoveries. Now I want to explore the deepest implications of this finding. What does it mean for humanity's future? What does it tell us about our place in the cosmos? And how should we understand this moment, the moment when we discovered that a potentially habitable world orbits the star next door? Because this discovery is not just a scientific achievement, it's a transformation in how we understand our cosmic situation, a revelation that the universe around us might be far more hospitable, far more interesting, and far more accessible than we ever dared to hope. Let me begin by considering what this discovery means for the concept of cosmic loneliness. For most of human history, we have felt alone. The stars were distant lights, beautiful but unreachable. Other worlds, if they existed, were unknowable, separated from us by gulfs so vast that they might as well have been in different universes. Even after the discovery of exoplanets began in the 1990s, this loneliness persisted. The planets we found were far away, tens, hundreds, thousands of light years. There were data points, abstractions, entries in a catalog. We knew they existed, but we couldn't truly know them. Alpha Centauri's planet changes this. This is not a distant world. This is the world next door. If the galaxy were a city, Alpha Centauri would be the house across the street. We are not separated by cosmic gulfs, but by cosmic steps, still vast by human standards, but tiny by galactic standards. For the first time, we have a specific, concrete neighbor, Not a theoretical possibility, but an actual world orbiting an actual star at a distance we can meaningfully contemplate reaching. This changes the psychology of our cosmic situation. We are not alone in an empty void. We have a neighbor. Whether that neighbor is inhabited or barren, living or dead, welcoming or hostile, we have a neighbor. This is profound. The feeling of cosmic loneliness that has haunted humanity might begin to lift. We are not the only island of matter in an empty sea. There are other islands close by, waiting to be explored. Now let me consider what this discovery means for the Fermi paradox. The Fermi paradox asks, if the universe is so vast and so old, where is everyone? If life is common and intelligence emerges frequently, why haven't we detected signs of extraterrestrial civilizations? The discovery of a habitable zone planet at Alpha Centauri adds new dimensions to this question. On one hand, it strengthens the case that habitable planets are common. If the nearest sun-like star has one, they must be abundant throughout the galaxy. This deepens the paradox. If habitable worlds are everywhere, the silence of the cosmos becomes more puzzling. On the other hand, the discovery provides a specific target for SETI, the search for extraterrestrial intelligence. If we're going to detect signals from another civilization, Alpha Centauri is a logical place to look. The planet is close. Any signals would be relatively strong. The transmission delay is minimal. We have, in fact, been listening to Alpha Centauri for decades. No artificial signals have been detected. The system appears quiet, at least at the frequencies and sensitivities we've searched. What does this mean? One possibility is that the planet is lifeless. No life means no intelligence, means no signals. The silence is explained by absence. Another possibility is that life exists, but intelligence hasn't emerged. Microbial life, or even complex life without technology, would produce no detectable signals. The planet might be a thriving biosphere without anyone to build radio transmitters. Another possibility is that intelligence exists but chooses not to transmit. Advanced civilizations might have reasons for radio silence, avoiding detection, using technologies we can't perceive, or simply having no interest in communication. Another possibility is that intelligence once existed but is gone. Civilizations might have risen and fallen on Alpha Centauri's planet, leaving no trace we can detect from Earth. The Fermi paradox is not resolved by this discovery, but it is sharpened. We now have a specific nearby world to contemplate. The question, where is everyone, becomes, is anyone there just 4.37 light years away? Now let me explore what this discovery means for the future of space exploration. Humanity has always dreamed of traveling to the stars. Science fiction is full of starships, warp drives, interstellar civilizations spanning the galaxy. But for most of history, these dreams have seemed impossibly remote fantasies with no connection to practical reality. The discovery of Alpha Centauri's planet brings these dreams closer to reality. Not because the technical challenges have diminished interstellar travel remains extraordinarily difficult, but because we now have a destination. We know there's something there worth visiting. This is psychologically crucial. Interstellar travel is so challenging that it requires multi-generational commitment, decades or centuries of sustained effort. Such commitment is hard to maintain for abstract goals. But a specific target, a known world, a place we can name and describe, this can sustain motivation. Consider the history of exploration on Earth. The great voyages of discovery were motivated by specific goals, routes to known lands, searches for legendary places, quests for particular resources. Abstract curiosity alone rarely sustained such ventures. Concrete destinations did. The same dynamic applies to space. The moon was reached because it was a specific visible target. Mars is being explored because it's a specific potentially habitable world. Alpha Centauri's planet can serve the same role for interstellar ambitions. This doesn't mean we'll be launching starships tomorrow. The challenges remain immense, but the discovery changes the conversation. We're not just discussing whether interstellar travel is theoretically possible. We're discussing how to reach a specific destination, a destination that might harbor life. Now let me consider the technical pathways to Alpha Centauri. Several approaches have been proposed for interstellar travel. Each has advantages and limitations. The first approach is conventional rocketry, scaled up. Chemical rockets, like those that launched Apollo, are far too slow for interstellar travel. Even the fastest spacecraft we've ever built, the Parker Solar Probe, which reaches speeds of about 200 kilometers per second, would take over 6,000 years to reach Alpha Centauri. Nuclear thermal rockets offer better performance, but still not enough. A nuclear thermal rocket might achieve exhaust velocities of 1, 0, 20 kilometers per second, enabling faster travel within the solar system, but still requiring millennia for interstellar journeys. The second approach is nuclear pulse propulsion. Project Orion, conceived in the 1950s, proposed propelling a spacecraft by detonating nuclear bombs behind it. The explosions would push against a massive pusher plate, accelerating the craft. Orion could potentially reach 5 to 10% of light speed, reducing the travel time to Alpha Centauri to 40 to 90 years. This is within a human lifetime, barely. A person born when the ship launched might live to see arrival. But Orion has massive problems. The nuclear explosions would produce dangerous fallout. International treaties prohibit nuclear weapons in space. The engineering challenges are enormous. The third approach is fusion propulsion. Fusion rockets, using the same reactions that power the sun, could potentially achieve exhaust velocities of thousands of kilometers per second. A fusion-powered starship might reach 20% of light speed, making the journey to Alpha Centauri possible in 20 to 40 years. Project Daedalus, a British interplanetary society study from the 1970s, designed a fusion-powered probe for a one-way trip to Barnard's star. Updated versions, like Project Icarus, have refined the concept, but fusion propulsion remains speculative. We haven't achieved controlled fusion on Earth, let alone in a spacecraft. The engineering challenges are formidable. The fourth approach is antimatter propulsion. Antimatter, when it meets matter, annihilates completely, converting all mass to energy. This makes antimatter the most energy-dense fuel conceivable, far more potent than nuclear fission or fusion. An antimatter rocket could potentially reach significant fractions of light speed. The journey to Alpha Centauri might take only years, not decades. But antimatter is almost impossible to produce and store. Current particle accelerators produce nanograms per year at enormous cost. Containing antimatter without it annihilating prematurely is an unsolved problem. Antimatter propulsion remains in the realm of theoretical speculation. The fifth approach is laser propulsion. This is the concept behind Breakthrough Starshot. Instead of carrying fuel, the spacecraft is accelerated by an external laser array. Powerful ground-based lasers push against a lightweight sail, accelerating tiny probes to 20% of light speed. At this velocity, the journey to Alpha Centauri takes about 20 years. The probes would fly through the system, capturing images and data, and transmit the results back to Earth. Total mission duration, about 25 years. Breakthrough Starshot has received significant funding and attention. The concept is being actively developed. The challenges are immense, building powerful enough lasers, constructing sails that can survive the acceleration, miniaturizing spacecraft to gram scales, but none are obviously impossible. If Breakthrough Starshot succeeds, the Alpha Centauri planet would be its prime target. Within decades, we might have close-up images of another habitable world. Now let me consider what a mission to Alpha Centauri might actually reveal. Imagine it's 2070. Breakthrough Starshot has launched a fleet of tiny probes toward Alpha Centauri. 20 years later, they arrive. What do they see? The probes fly through the system at 60,000 kilometers per second, too fast to orbit or land, but fast enough to capture detailed images as they pass. The first images show Alpha Centauri A and B as resolved disks, actual stars, not points of light. The binary nature of the system is vividly apparent. Two stars locked in their 80-year dance. Then the planet appears, a tiny crescent at first, growing larger as the probes approach. The images resolve surface features, continents, oceans, clouds, whatever exists there. If the planet has oceans, they would appear as dark, smooth regions reflecting less sunlight than land. Continents would be brighter, perhaps with color variations indicating different surface compositions. Clouds would appear as white patches drifting across the surface. If the planet has an atmosphere, spectroscopy during the flyby would reveal its composition. The probes carry spectrometers analyzing the light passing through the atmosphere as the planet passes in front of its star from the probe's perspective. If the planet has life, signs might be visible. Vegetation might produce characteristic colors, a red edge like earth plants, or something entirely different. Artificial structures, if they exist and are large enough, might be detectable, though this is speculative. The probes transmit their data back to Earth. At light speed, the signals take 4.37 years to arrive. In 2095, humanity receives its first close-up views of another potentially habitable world. This is science fiction today. But the physics is sound. The engineering is challenging but not impossible. The discovery of Alpha Centauri's planet makes this future more likely and more desirable. Now let me consider what colonization of Alpha Centauri might eventually look like. Sending tiny probes is one thing, sending people is another. But if we think on timescales of centuries, human colonization of Alpha Centauri is not impossible. The challenges are immense. A crewed starship would need to sustain human life for years or decades. It would need to accelerate to significant fractions of light speed and then decelerate on arrival. It would need to carry everything required to establish a self-sufficient colony or the capability to manufacture what's needed from local resources. Generation ships are one concept. A spacecraft large enough to support a population for multiple generations would travel at modest speeds, perhaps 1 to 5% of light speed, taking 100 to 400 years to reach Alpha Centauri. The passengers who arrive would be the descendants of those who departed. Suspended animation is another concept. If humans can be safely placed in some form of hibernation, the subjective duration of the journey could be reduced. Passengers would sleep through most of the voyage, awakening on arrival. Advanced propulsion might enable faster travel, reducing the need for generation ships or hibernation. If fusion or antimatter drives become practical, the journey might take only decades long, but survivable for a single generation. Whatever the approach, establishing a colony would require landing on the planet if it's hospitable, or constructing habitats in space if it's not. The colonists would need to become self-sufficient, unable to rely on supply ships from Earth that would take years to arrive. This is a project for future centuries, not for our lifetimes. But the discovery of a potentially habitable destination makes it conceivable there is somewhere to go. Now let me explore what interstellar colonization would mean for humanity. If humanity establishes a presence at Alpha Centauri, we become a multistellar species. Our existence would no longer depend on a single star. Even a catastrophe that destroyed Earth would not end humanity. We would persist at Alpha Centauri. This is the ultimate insurance policy. A species confined to one star is vulnerable to extinction. Supernovae, gamma ray bursts, rogue black holes, rare but possible events could sterilize our solar system. A multistellar species is far more resilient. But there are deeper implications. Communication between Earth and Alpha Centauri would be limited by the speed of light. A message would take 4.37 years each way. Conversations would be impossible, only exchanges of information separated by nearly a decade of delay. This means an Alpha Centauri colony would be largely autonomous. Decisions couldn't wait for Earth's approval. The colonists would develop their own governance, their own culture, their own identity. Over time, the colony might diverge from Earth, biologically, culturally, politically. The distance would create isolation. Isolation would create differentiation. Earth and Alpha Centauri might become separate civilizations, related but distinct. This has happened before in human history. Colonial settlements have diverged from their homelands, developing unique characteristics and eventually independence. The Americas diverged from Europe, Australia diverged from Britain, Alpha Centauri might diverge from Earth. In the very long term, thousands or millions of years, this divergence might extend to biology. Different environments exert different selective pressures. Humans at Alpha Centauri might evolve differently from humans at Earth. We might become separate species. This is unsettling to contemplate, but it's also magnificent. Humanity would not just survive, we would diversify, spreading across the stars, adapting to new environments, evolving into forms we cannot imagine. The discovery of Alpha Centauri's planet is the first step on this path. There is a destination. There is a reason to go. The journey of 1,000 light years begins with a single star system. Now let me consider what this discovery tells us about the nature of life in the universe. Every exoplanet discovery teaches us something about how planets form and where they exist. But habitable zone planets around nearby sun-like stars are especially informative. The fact that Alpha Centauri A has such a planet suggests that habitable zone planets are common. Alpha Centauri is not a special star, it's a typical member of its stellar class. If a typical star has a habitable zone planet, many stars do. Extrapolating from this single data point is risky, but combined with the thousands of exoplanets discovered by Kepler and other surveys, a picture emerges. Habitable zone planets are not rare. They might orbit a significant fraction of Sun-like stars. This has profound implications for the prevalence of life. If habitable planets are common, and if life arises readily on habitable planets, then life should be abundant in the universe. The cosmos would be teeming with organisms, mostly simple, perhaps, but living nonetheless. The alternative, that life is rare, remains possible. Perhaps the origin of life requires very specific conditions that most planets don't have. Perhaps habitable planets are necessary but not sufficient. The existence of a habitable planet doesn't guarantee life. The Alpha Centauri planet will help resolve this question. If we detect biosignatures there, life is clearly common. It exists on the first habitable planet we've been able to study in detail. If we don't detect biosignatures, despite favorable conditions, life might be rarer than we hoped. Either answer transforms our understanding of our place in the cosmos. Now let me reflect on what this moment means, the moment of discovery. We are living through an extraordinary time. Within a single human lifetime, we have gone from knowing of no planets beyond our solar system to knowing of thousands. We have developed telescopes capable of studying the atmospheres of distant worlds. And now we have discovered a potentially habitable planet orbiting the nearest sun-like star. Future generations will look back on this era as a turning point. The moment when humanity looked outward and found that the cosmos was not empty but full of worlds. The moment when the question, "Are we alone?" began to transition from philosophy to science. The detection of Alpha Centauri's planet is a milestone in this journey. It's not the first exoplanet that was discovered in 1992. It's not the first habitable zone planet, many have been found, but it's the closest such planet, the most accessible, the most studied. This is the planet we might visit. This is the planet we might colonize. This is the planet that might answer definitively whether life exists beyond Earth. The significance cannot be overstated. For millennia, humans have looked at the stars and wondered. Now we know that at least one of those stars, the closest sun-like star, has a world where life might flourish. We don't yet know if life exists there. We don't know what we'll find when we look more closely. But the possibility is real. The investigation is beginning. The answer might come within our lifetimes. Now let me consider the philosophical implications of this discovery. The existence of a potentially habitable world at Alpha Centauri raises profound questions about meaning, purpose, and our place in the universe. First, it suggests that habitable conditions are a natural feature of the cosmos. The universe produces planets in habitable zones around stable stars, not as a fluke, but as a regular occurrence. Habitability is not special, it's normal. This challenges certain views of human significance. If habitable worlds are everywhere, Earth is not unique. Our planet is one of many, perhaps billions, where conditions permit life. Some might find this diminishing. We are not special, we are typical. The cosmos doesn't revolve around us. We are one small instance of a common phenomenon. But others might find it ennobling. We are part of a cosmic pattern. The universe naturally produces places where life can emerge. Our existence is not an accident, but an expression of the universe's tendency toward complexity and awareness. Second, the discovery raises questions about cosmic purpose. Is there a reason the universe produces habitable worlds? Is there a direction to cosmic evolution, from simple beginnings to complex outcomes like life and intelligence? These are questions science cannot answer directly, but the discovery of habitable worlds provides data for the discussion. The universe is evidently structured in a way that allows, perhaps encourages, the emergence of life. Whether this has deeper significance is a question for philosophy and religion. Third, the discovery challenges us to consider our responsibilities. If there is life on Alpha Centauri's planet, do we have obligations toward it? Should we avoid contamination? Should we attempt contact? These questions are not merely academic. Future missions to Alpha Centauri will need to grapple with them. The ethics of interstellar exploration are not yet well developed, but this discovery forces us to begin thinking about them. Fourth, the discovery invites us to expand our moral circle. Currently, our ethical concerns focus on humans and perhaps to some extent on other Earth life. But if life exists elsewhere, especially intelligent life, our moral concerns might need to expand. This is challenging. We struggle to treat all humans ethically. Extending ethics to extraterrestrials seems almost impossibly difficult, but the discovery of nearby life might force the issue. Now let me consider what we should do in response to this discovery. The detection of Alpha Centauri's planet is not just a scientific finding, it's a call to action. It demands a response. First, we should prioritize the characterization of this planet. James Webb and future telescopes should dedicate significant resources to studying its atmosphere, searching for biosignatures, and understanding its nature. This is the most important target in exoplanet science. No other planet combines proximity, habitability, and accessibility. The scientific return from studying Alpha Centauri's planet will exceed that from any comparable investment. Second, we should accelerate the development of interstellar propulsion. Breakthrough starshot and similar concepts should receive increased support. The technical challenges are great, but so is the potential reward. The existence of a specific, valuable destination changes the calculation. Interstellar travel is worth pursuing not as an abstract capability, but as a means to a concrete goal. Third, we should begin planning for contact. If Alpha Centauri's planet hosts intelligent life, we might eventually communicate with it. What would we say? Who would speak for humanity? How would we handle responses? These questions are speculative. We have no evidence of intelligent life at Alpha Centauri. But the discovery of a habitable planet makes them more relevant. Planning should begin now, even if implementation is decades or centuries away. Fourth, we should educate the public. This discovery has implications for everyone, not just scientists. The public should understand what has been found, what it means, and what might come next. Scientific literacy about exoplanets and the search for life is crucial. Informed citizens can participate in decisions about exploration priorities, ethical guidelines, and resource allocation. Democracy functions best when the public understands the issues. Fifth, we should contemplate our place in the cosmos. The discovery of a nearby habitable world is an invitation to reflection. What does it mean to share the universe with other worlds, perhaps other life? How should this knowledge shape our values, our priorities, our self-understanding? These are not questions with immediate answers, but they are questions worth asking, questions that the discovery forces upon us. Now let me bring this exploration to a close. James Webb has detected a planet orbiting Alpha Centauri A. This is the closest exoplanet ever found around a sun-like star. It is located in or near the habitable zone, where conditions might permit liquid water and life. This discovery is not an ending, but a beginning. We do not know what this world is like. We do not know if it has an atmosphere. We do not know if it harbors life. We know only that it exists, that the star next door has a world worth investigating. The investigation will take years. James Webb will study the planet's spectrum, searching for atmospheric gases. Future telescopes will refine our understanding. Eventually, perhaps, spacecraft will visit, sending back humanity's first close-up images of another habitable world. What will we find? I cannot tell you. Perhaps a barren rock, lifeless and silent. Perhaps a Venus-like hothouse, sweltering under thick clouds. Perhaps a Mars-like desert, cold and dry. Or perhaps most thrilling of all, a world with oceans and atmospheres, with weather and seasons, with chemistry that hints at biology. We don't know, but we will find out. The cosmos has given us a gift, a destination, a target, a neighbor. It is up to us to explore it. The closest exoplanet ever, a world 4.37 light-years away, orbiting the sun's nearest sun-like neighbor, close enough to study, close enough to visit, close enough to dream about. For all of human history, we have looked at the stars and wondered. Now we know that at least one of those stars, the one right next door, has a world that might, just might, be like our own. This changes everything. It changes how we think about the cosmos, how we plan for the future, how we understand our place in existence. We are not alone in an empty void. We have a neighbor. The discovery of Alpha Centauri's planet is a watershed moment. Centuries from now, historians will mark this as the beginning of humanity's interstellar future. The moment we found somewhere to go, the closest exoplanet ever, and it's waiting for us.